So I just wanted to give you some highlights of the progress on the initial seed project on clathrate hydrate energy storage materials. And the key accomplishments that we've had this year are 6 papers just within the year in high-impact journals, including Science, the Journal of American Chemical Society, the Journal of Physical Chemistry, Chemical Physics Letters, and Applied Physics, and also cover articles in Chemical Physics Letters and the American Institute of Chemical Engineering Journal. All of these based on work funded by the RMERSEC. And as I mentioned, we have training of postdoctoral and undergraduate students, as well as international collaborations, and NREL collaborators are very important in this project. And we're focused on the new synthesis and understanding mechanisms of clathrate hydrate materials for storage. Well, why are we doing this? Well, the motivation is because the current DOE targets places the amount of hydrogen to be stored as 5.5 weight% by 2015. This is the revised DOE target as of earlier this year. And as yet, this has not been achieved by any material. In addition, the storage aspect of this project is where we believe transformative research can occur, and is really a key part of the renewable energy materials portfolio. So why are we interested in using clathrate hydrates in particular? Well, firstly, they're mainly composed of water, so around 85% of this material is water, and so the idea is that the major byproduct would be water. It also offers potential for reversible storage of the fuel and also controlled hydrogen release. So in order to release the hydrogen, you either just decrease the pressure slightly by, for example, just turning a valve, or increase the temperature just above the stability temperature, and you can release the hydrogen at near ambient conditions. So the theoretical hydrogen storage capacities of these clathrate materials is illustrated in this table here, where the structure 6 clathrate hydrate, you see, exceeds the DOE targets, and then with these other structures, the structure 2 being the most common, ranging from 3.8 to 5 weight% depending on the model of the occupancy of the small cage. So in essence, this table illustrates that the clathrate hydrates could approach the DOE targets. And in addition to that, we've also recently shown a first proof of concept of a clathrate hybrid technology in which you can have hydrogen stored in the clathrate cages as well as hydrogen from the host material itself. And this is work that was in collaboration with Andy Herring's group. So we actually were able to, in this system, have hydrogen stored within the clathrate cages and then use the host to power a fuel cell. And using this kind of clathrate hybrid technology, we could potentially increase the storage capacity by around 300% or more. So some of the compounds we recently synthesized are hydrogen in the tertiary butyl amine hydrate. If you recall, the structure 6 hydrate was the one that exceeded the DOE targets, and so we're looking at this compound, and we're the first to show that hydrogen could be stored in this system. And we also observed that there was a structural transition from structure 6 to structure 2, and this was just recently published in the Journal of Physical Chemistry A. We're able to characterize these materials, in other words, determine how much hydrogen is actually in there and the environment that this hydrogen is in. So whether it's in a cluster with 4 hydrogens in the cage, or 3, or 2, or even 1. And we can do this very nicely in the laboratory using in situ Raman spectroscopy, because from the hydrogen vibron peaks, it gives us a really nice fingerprint, and the peaks just shift depending on the occupancy and the environment. We also looked at this same system, the tertiary butyl amine system, with methane for storage, and this was another paper that we just recently published, again in the Journal of Physical Chemistry. This just shows the storage capacities with methane. And again, this particular system also showed this structure 6 to structure 2 transition under certain conditions.